everyone. Thank you very much for coming to my talk, which is called Attacking Edge through the JavaScript compiler. So just a quick words about me. I got started in security 3 years ago now by playing CTF with the Eat, Sleep, Run, Repeat team. And I quit my job last year to do VR full-time. I've mostly been doing JavaScript engines, focusing on JIT compilers for all the engines. Chakra was my main target up to a few months now. And this is my Twitter handle if you want to. I intend to release everything, like the slides and the exploit code, within a week or so, so I'll probably publish it on Twitter. So the agenda for today, I tried to make the talk accessible to anyone, those that do not have any kind of experience with JavaScript engines and those who do. So we'll do a quick intro of what's Chakra Core, some primer about JavaScript engines, and some of the internals basics. And then we'll go into just-in-time compilation and the problematic of just-in-time compilation for JavaScript. And then I'll talk specifically about the JIT compiler that's inside Chakra, and we'll finish by walking through an exploit that I submitted to MSRC last year. So quickly, what's Chakra Core? So you probably know Edge is the default browser on Windows 10 now. Chakra is the name of the JavaScript engine that powers Microsoft Edge. And basically, Chakra Core is the open source version of Chakra, which, as far as I know, is basically 95% of the thing, minus a few things such as COM API, Edge bindings. And Chakra Core is available on GitHub, so you can just look at the code. And it's written mainly in C++. And yeah, that's about it that there is to say about it. So a quick primer about JavaScript engines, so that everyone can be on the same page. So these days, what makes up a JavaScript engine, you have kind of these 5 main components that you will see in the 4 major engines, so Chrome, Safari, Firefox, and Edge. So the first thing you have is basically the parser. It's the entry point of the engine. You basically feed it the source code. It passes the thing, produces an abstract syntax tree, and produces custom bytecode. That custom bytecode, which is specific to each engine, is then fed to the interpreter, which is basically a virtual machine that will execute that bytecode. That relies on what I call the runtime, which basically provides all the basic data structures, implements the built-in functions of JavaScript, etc. You, of course, have a garbage collector because you don't have to free memory and do memory management in JavaScript. And you might have one or many JIT compilers. So this varies for each engines, but at least you have one these days. So now, quickly, some internals of Chakra Core that we'll need throughout the talk. So in all JavaScript engine these days, basically everything that you have in your JavaScript code is internally represented as something called a JS value. In Chakra, every value basically has the same type, which is just like a void pointer, which is called a var. Chakra uses a trick that you find also in other engines, which is basically nan-boxing. It's a trick where you basically, in 8 bytes, you can encode some kind of type information as well as the value itself. So how that looks like is basically, in Chakra, if you take the integer x41414141, it is represented internally as the thing you have on the right, which is 414141 with the 48th bit set. And if you take a double, which has the same hexadecimal representation, you find the same thing, 414141, but XORed with the FFFC. So basically, they use the fact that on x64, the upper 17 bits are cleared for user space addresses to encode some kind of type information there. And what that means is that if none of those bits are set, you're basically dealing with a valid pointer, and dereferencing that pointer will basically lead you to the actual object, which will contain more information. So those objects, commonly referred to as JS objects in all the major engines, we'll talk about them now. So JavaScript objects, they're basically a dictionary, so it's a collection of key value pairs that are called properties. The interesting thing to note is that each object does not maintain its own map of property names to property values, and this is something that all JS engines do these days. The object will only maintain the property values, and as basically a pointer to an object which will basically describe that object layout. So in Chakra, it's called the type, and it allows for 2 nice things. The first one is you save space, because every object of the same type, basically, you only allocate the type allocate the type once, and you have all the objects pointing to the same type. And it also allows for optimizations such as inline caching, and we'll talk more on that later. So object layouts in Chakra, so you have two object layouts basically. This is the most default one. I realized this morning that the code might be a bit small for the ones at the back, so I hope you'll be able to follow along. So basically here I declare an empty object and set two properties on it, x and y. Those are integers, x for 1 for 1 for 1, and x for 2 for 2 for 2. And if you look in memory, this is the layout that you'll have. You basically have the vtable pointer, the type pointer, which is what I talked about previously, and you basically have this oxlots pointer, and if you dereference that pointer, is basically where you will find your property values in memory. So it's basically a pointer to a contiguous memory region where you will only have the property values and not the property names. So if, like here, you can see that it points to our properties. We also have another layout that's used throughout Chakra, and it's also a common optimization. So here I declare an object, but I declare the properties directly in it, so it's a scalar object. And here they use a layout that they call object header inline, and basically what that means is they don't use the extra pointer to store the property values, they store it directly inline into the object itself. So how property access basically works? Well, as I said, all the Chakra objects will basically have something called a type, and when the runtime has to deal with a code that accesses a certain property, so here I'm setting property X on an object and just printing it, well, the runtime will basically call a class method on the type saying, get me that property for that certain property name. So internally, it's called the property ID if you want to look in the code. And that type is basically able to say, oh, property ID is at this certain index, and we'll return the thing. So here, if we query the type, it will return oxlots 0, because that's where a.x will be. So yeah, that's about it for the internals that we'll need. There's a lot more. There's more to talk about, of course, but I don't have time to spend too much. But that's all we'll need going forward. So now we'll go into the core of the subject, which is JavaScript JIT compilation, and especially like the problem associated with it for JavaScript. So basically, what is the goal of JIT compilation is it's basically to generate highly optimized machine code. The upside of it, of course, is that your code runs like way faster than when it runs in the interpreter. But you have two problems that you have to deal with. The first one is higher startup time, because you don't want your web page to take 10 seconds to load. And you also have no type information. JavaScript doesn't have type information. So we have to deal with that somehow, and I'll try to shed some light on that later on. So in practice, what you have is basically your JavaScript code will start running in the interpreter, and if something gets called repeatedly, it will then be scheduled to be compiled and be compiled to machine code, and then you'll run actual machine code. So I try to have a lot of examples. So this is the first one we'll look at, which is addition. So I have a function that basically takes two parameters, x and y, and returns the addition of the two. And you've probably all seen some of the memes about JavaScript addition being quite obscure and behaving weirdly. And if you look at the standard that defines the JavaScript addition, this is basically what you have. So you don't have to read everything, but like something as simple as the addition, like has all these steps that you have to take if you want to implement it. So now the question is, do we really want to generate machine code that does that? Well, the answer is no, because this is basically what you already have in the interpreter. So if you were to have any kind of performance gain, it would be pretty marginal. So we need to be smarter than that. So the truth is, if you have a function called addition like that, realistically, like more than likely, you're going to only call it with like integers, like that, and that's kind of what the JIT compiler will rely on. So here, assuming I only call the function addition with integers, I probably want something that's as close as the assembly code that I have here, which is basically two instructions, just like add the two registers that hold the parameter values and just return. But we don't have type information, right? We don't know that those things are going to be integer, which is like the main problem of JavaScript just-in-time compilation. So the way the JIT compilers basically deal with that is that while we are running in the interpreter, we will collect profile information on the type of parameters, and we will generate optimized code based on that. And so more on that later. I have another, oh yeah, sorry. So here I call the function repeatedly in a loop. I is going to be an integer, 1000 337 is also an integer. And every time we call that function, the interpreter collects type information saying, oh, x is an integer, y is an integer. And every time we run the loop, we call that, up to the point where we'll actually say, oh, this thing has been called a lot, let's JIT compile it. So the JIT compiler will basically make the assumption that we've only seen integer parameter for that function, so more than likely the parameters will continue to be of the same type. And the idea is that the JIT compiler will check the type of the parameters at the beginning to make sure that it's what we assume they will be, and the code will be generated based on that assumption, which is why it's called speculative compilation, because we speculate on the type of the parameters. So I have another example here. I have a function called getX. Pretty simple. It takes one parameter and returns property x on the thing. So more than likely, if you have this function, you expect to only give it an object. And here I call it in a loop repeatedly with a scalar object which only has property x. And the key here is I only call it with the same scalar object every time. So the thing will have the same layout in memory. But object lookup is a bit complex, right? You have to go through the type, you have to query the type to know where the property lies. And you don't want to compile down that whole logic because then you don't gain anything. It's basically code that's already implemented in the interpreter. So here, same thing. We will basically speculate on the type of the parameter, assume that if we've only seen one particular type, then we will generate code for that particular type, and then we'll be able to use direct memory access. And this is what's called inline caching. We'll see that in details later on. And if the code gets an object of a different type when it's JIT compiled, then we'll basically have to fall back to the interpreter because the code won't be valid for other types of objects. So that takes us to two key concepts that I use in JIT compilation. The first one is so-called slow path. So basically, as I said, speculative compilation will make assumptions. Those assumptions need to be checked in the code. And if something does not hold, you might have to go back into the interpreter. So that's true for addition, right? Like, if we generate JIT code for addition of two integers and then we have like two strings, then we need to do something completely different. So we have to fall back into the interpreter via a slow path. The bad news for that is you get a performance hit because you exit the JIT code. The good news is that it was actually intended, so for that particular operation, you will go back to the interpreter, which is much slower, but you will still return to a JIT function. The second key concept is called bailout, and basically, sometimes if your assumption does not hold, well, the slow path is not going to cut it because your code is complete garbage. So for example, for my function getX, an object is a pointer. What if I give it an integer? Well, integers are tagged. It's never going to be a valid pointer, so if we don't bail out, we'll just most likely end up crashing at some point in the JIT code, so you don't want that. And then in that case, like the whole execution of the function has to basically resume into the interpreter. The downside of that is now it's a big performance hit because bailing out is a non-trivial process. And the only upside I can find is basically you probably, like if you're not familiar, you'll probably never realize that your engine was actually doing that, which is a good thing. So it actually works, which is it's pretty insane to me. So to summarize, JIT compilation of JavaScript, you rely on profile information that you collect while you're running into in the interpreter. The optimized code is generated based on basically that information, and the key takeaway is that your JIT code has to be responsible for checking that the assumptions that you're going to make actually hold true, otherwise you will have bad surprises. And so basically problems, whether it's security issues or just like random crash will basically arise when the engine assumes something that is not true. And that's the whole game as security researchers looking for bugs in those JIT engines. So now we'll get to talk about Chakra's JIT compiler specifically. So the Chakra JIT pipeline, how it looks like roughly. So nothing crazy. You have an interpreter. It keeps track of how many times the function has been called. And past a certain threshold, it will just schedule the thing for JIT compilation. So what that means is that each function object has an entry point. It will swap that entry point to a func that basically will schedule JIT compilation. The interesting note is that compilation happens out of process in Edge. Basically, they move the whole JIT compiler to its own process so that the content process can have arbitrary code guard, which prevents mapping read-write execute memory. And basically, when code generation is done, the JIT server will basically notify the content process, and you will change the entry point to the native code address. So the next time the function is called, you will be actually running the JIT code. Chakra has only one JIT compiler, which is two-tiered. The two names are simple JIT and full JIT. For the purpose of this talk, we'll only focus on full JIT because simple JIT is not super interesting from a security researcher point of view. It's pretty standard. It operates on a control flow graph and a custom IR, which is generated from the function's bytecode. The interesting bit here is that the bytecode is basically as a format that's optimized for the interpreter use case, which might not be the best thing for the JIT compiler. So you will find in other engines that you might have basically a transpiling phase from the interpreter bytecode to an IR that's most suited for a JIT compiler. And the main steps of compilation are roughly, so I have the list here. You basically build the IR, this is the IR build the phase, then you do the inline phase. It always happens quite early in the process because inlining allows for further optimization. So if you look at other JIT engines, you'll probably see that it happens super early in the process. Then the FG build phase, which basically builds the control flow graph. And then we have the globopt phase. So it's short for global optimizer. It's where most of the magic happens and what we'll be focusing on. And then you have other phases and which basically start to be mesh independent up until the lower phase. Everything is done independently of the architecture we're dealing with, to some extent. And yeah, as I said, the global optimizer is what interests us the most. If you're going to look for bug or have looked for bug, more than likely that's what you've looked at, because that's where most of the bugs are actually lying. So I have some example. Once again, I do apologize for the back of the room. I hope you'll be able to follow. So here, basically, we'll see two examples. On the left, I have the JavaScript code. Here, I have a simple addition function that we talked about. Just returns the sum of the addition of the two parameters you give it, x and y, and the function is called with integer parameter. And on the right, we have basically what is generated by the JIT compiler with some kind of high-level assembly. And I'll walk through what is generated so that I can highlight some of the concepts I talked about. So here, highlighted in red, you have the intermediate representation of the instruction that we're looking at. If you cannot see on the right, the instruction is basically called add A, which is basically add those two things, S2 and S3, which are symbols which basically represent the parameters x and y, and the addition of that is put into S0, which is the special symbol for the return value. And I don't know if you can see, but the symbol have an annotation between brackets, which is likely can be tag value integer. And this is what comes from the profiling phase. This is the profiling information that we got from the interpreter, saying the thing can be a tag value and some kind of hint that says it should be an integer. So the first thing that code does in terms of assembly, it actually checks that x and y are actually integers. The way it does that is that, as I said, integers are represented with the 48-bit set, so it will just shift the value to the right with a certain constant, do a binary OR on the two, and compare that to a constant. So it's a cute optimization to basically check the two in with one snippet of assembly. And if basically that fails, we can see that we have some jumps to that label 4 thing. And on that label 4, we basically see that it does a call operation add full. And this is the slow path I was talking about. In case we're not dealing with tagged integer, the code we generated is basically garbage and not going to be, it's basically either going to be faulty in terms of semantics or faulty in terms of if it will crash the process. So here we have to go back into the interpreter, and this is exactly what we're looking at now. Calling up add full will actually go back to the interpreter for that particular thing. But we see that we return afterwards, right? So this is what I was talking about. Slow path, it's not ideal, but it's still okay. And here, highlighted, I have the code in case the assumption actually was true, which is that the two things were actually integer. And then we can see that it's pretty straightforward. It just does an add operation in x64, put that into the return register, and we're basically done. So the interesting thing to see here is basically, if the check is successful, then we basically only have 7 to 8 assembly instructions that are being run. So from the addition thing, which is 10 high-level operations in the standard, we actually have something which is 7 to 8 assembly instructions. So that's why it gets super fast. Now I have the same thing, but this time with an object to illustrate other concepts I talked about. The function is also an addition function, but this time, instead of adding two parameters, you only give it one parameter, which is an object, and it adds property x and y. And I call it repeatedly with an object that has those two properties, x and y, but the same layout. This is the important thing. So the interpreter will basically profile, will have profile information that the function was called with only one type of object, and we'll optimize based on that. So we'll look once again at what was generated to illustrate some of the concepts. So the first thing we do is check if we are dealing with a pointer. So once again, it's pretty simple. As I said, a pointer will have the upper 17 bits cleared. So the first thing it does is it shifts the value right by 48, checks that the thing is actually 0. And if it's not, then we see that we have a call to something called save all registers and bailout. And that basically means, like, I'm not able to handle that type of parameter. Like, this has to go back into the interpreter. And this is like the really costly thing that you want to avoid if you like trying to write performant JavaScript code. Then, basically, like another interesting thing to see, if you're looking at Chakra specifically, is that the annotation was the thing likely can be a tagged value with hint object. But since we actually now check that the thing was actually not a tagged value, we can see that the annotation has changed, and now it's marked as being likely object. So this illustrates a concept I will talk a bit more later on, where basically, based on what we've run so far, we have updated type information, which is more refined. Here we know we are dealing with a pointer, which is most likely a regular JavaScript object. And here, basically, we have the check for the type. We basically fetch the type of the JavaScript object, and we check that its value is equal to the one we profiled. Here we have another slow path, as I said, which is if the type is not the same, maybe for some reason it still is equivalent in terms of where the properties are stored. So we might have two different type objects, but property X is at offset 0, property Y is at offset 1, in which case we can use the JIT code. So we basically try to salvage things instead of bailing out. If we cannot, we just bail out. And here we get to the really interesting part, which is if the checks were actually successful, then we know precisely where property X is stored. So here we have a direct memory access to fetch property X. So we fetch from offset 16, which is where the property X will be. And now when we fetch O.Y, we see that we only have one assembly instruction, which is this time fetch from offset 24 of the object, which is where property Y will be. So the interesting thing here is that, once again, if all the assumptions actually held true, then you don't execute a lot of assembly instructions to actually check that the thing is correct, and then you have direct memory access to fetch the object property itself. And also, we can also note that for the second property access, we don't run the checks again, which is pretty smart, right? Because we know that in between the two instructions, the type shouldn't have changed, so we don't have to recheck again that the thing is actually a pointer and that this is of the type we profiled. And I'll try to explain a bit how basically Chakras does it. So most of the magic happens in the global optimizer. It's a 3-pass process on the CFG, one backward pass, one forward pass, and another backward pass, which is called the desktop pass. The backward pass algorithm is in backwardpass.cpp if you want to look at it. It's about 9,000 lines of code. And the forward pass is in a bunch of files that are prefixed with globopt, and this is about 30,000 lines of code. So as you can guess, this is what we really care about. And the entry point is in globopt optimized if you want to look at it yourself. So the backward pass is not the most interesting for us. The algorithm, in essence, is pretty simple. You go over each block backward. For each block, you go over each instructions backward. Information is gathered for each block, and every time you start processing a new block, you merge the information of all the successor block that you've already processed. And it can perform some like simple optimization, like instruction rewriting and that sort of stuff, but it's not, like from a security standpoint, it's not important for us. And the forward pass, so I will spend some time on that because this is what we really care about. The algorithm is the reverse, so you go over each block of the CFG forward, and for each block you go over each instruction forward. And same thing, data is gathered for each block, and every time you start processing a new block, you basically merge the information that you have from all the successor blocks. So sometimes you have one block, but sometimes you have multiple, so you have to merge information. And this is what basically will perform most of the magic that will lead to really optimized code. And here I have an example that I want to walk you through. It's really minimalist, but it's kind of to give you a feel of how things are performed in the forward pass if you want to look at the code yourself. And this is also basically what you will see in other engines to some extent as well. So here I have the same function addition with an object, and on the right we have the intermediate representation of that function, which is basically 3 intermediate instructions. two load fields, so load property X, load property Y, and add the two together. And this is the output right before we do the forward pass. And after the forward pass, we have this thing on the right that's totally unreadable, like took me like 4 months to be able to decipher it, and it's redacted, like it's actually even more obscure than that in reality. The thing here I want to show you is that basically, for some reason, like the thing has been completely transformed, and we have a lot more of annotations going on and stuff like that. So, like, you know, a lot of things actually took place in the forward pass. And the question is, what actually happened here? So, I kind of want to try to highlight what happened. So, as I said, you know, the forward pass will go over each instruction. Each instruction will basically go through that function, which is called opt instruction. And opt instruction will basically call a whole bunch of functions, like 30 to 40, if I recall correctly. Passing that instruction, and all the methods in the forward pass are only going to deal with like a subset of all the IR instructions that exist. So you have switch statements everywhere. And one of those functions is called optimize tag checks. And if we look at the code, then we'll see that we basically have a switch statement, and we actually have a case for when the op called is a load field, which is what we're dealing with now. So like that function actually will be able to do some things on that particular instruction. So if we look further at the code, there's a bunch of things happening. First off, it retrieves all the type information it has for that particular value at the block we're dealing with. And then we can see that highlighted on the right, we have a check, an if statement. If value type can be tagged value. And if this is true, then we execute new code. And the first time we run through that thing, it will actually be true because we profiled that the thing can, you know, it's most likely an object, but it still can be a tagged value because we don't have any certainty at this stage. So the check is true, and we'll basically do two things, which is the first one, we'll insert a new instruction, which is bail on not object. This is what we've seen before, the first check that you saw at the beginning, where, you know, it checks that the thing is an object, and if not, it just completely bails out. And then we update the value type, because now since we inserted a check to check that the thing is actually an object, we know that going forward, the thing is most likely, like, it's definitely a pointer, so we update in the thing. It cannot be a tagged value anymore. And now the cool thing is that when you process the second load field instruction, you end up following the same code path, but this time the check will actually return false. And this is to highlight the fact that the forward pass, basically every time it deals with an instruction, all the methods will be either able to refine the type information, which will lead to more optimization, or in some cases they will have to loosen type information because, you know, things can, you know, JavaScript is a complex language, you have callbacks and everything, so you have to be mindful of that. So there's of course a lot more happening. My hope is that this example kind of gives you a rough idea of, you know, like how things are done. You have to keep in mind that it's like 30,000 lines of code, so, you know, like there's a lot of methods that deal with only certain instruction. The load field one I highlighted is probably one of the simplest operation. And yeah, it's to give a rough idea basically. And I'll introduce two key concepts that I use throughout the Chakra JIT compiler to basically perform the optimization right now. So the first one is called symbol liveness. If you've done like some data flow analysis and stuff like that, you probably know that term. It's what the Chakra team uses as lingo as well, so you will find those words in the code. And we take the same example, like, you know, we add two object properties together. And here, property X will be in my aux slots array at offset 0, property Y will be in my aux slots array at offset 1. And if what you expect from your compiler is that the compiler will be smart and, you know, will see that it will dereference the same array twice at two different offsets. So you expect that the compiler will only load the array once, the array pointer once, and then just dereference that 2 times. So you probably expect assembly code that's as close as what I have here. So how does the forward pass is able to do that is basically using symbol liveness. When it will optimize the first property access, o.x, it will basically set the symbol associated with the aux slots pointer of O as live going forward. And what that means is that with that information, when we deal with the second instruction, we're now able to see, oh, this thing is live. So when we generate the code, this thing is live. I don't have to actually reload it. I can just reuse the value that was there already. And this is how the JIT compiler is able to, you know, come up with those kind of optimization when you access the same array over and over again. Now the counterpart to that is that if we change the example slightly, and in between the time we fetch property X and we fetch property Y, we have some operations, and those operations might cause the property value array to be reallocated, what do we have to do in that case? Well, you don't want to use a previously fetched value because you would then read from free memory. Maybe you do if you're looking for bugs, but the Chakra developers probably don't want that. And so you have to use the counterpart mechanism, which is called the kill mechanism. Once again, this is Chakra lingo. That's what they use in the code. Which basically, in essence, is if you deal with an instruction that might, for example, cause that particular object to be reallocated, then the JIT compiler has to kill the symbol associated with it to basically say, going forward, this thing might have been completely changed, so you cannot reuse what you previously had. So that's basically when you lose refined information, and that's basically when you have those situations, you will basically miss some optimization opportunities. And this is basically like those two mechanisms. Like this is a really basic introduction, but this is what you'll see throughout the code everywhere. And if you follow closely some of the bugs reported by LookYard, or sorry, my bad, mostly with arrays, those basically they have to do with that particular mechanism of type information and not being killed properly under certain conditions. So maybe if you look at those bugs again, it will make more sense. So the forward pass sounds simple enough, right? Well, the truth is all the examples I showed you are really simple because there's only one block in reality. JIT code has to deal with complex constructs in terms of CFGs, so such as loops, because loops have information that is true only the first time you run it, so before you run the loop body, and then you have information that is also true all the subsequent iterations of that loop because you run the body once. You have conditional statements, which introduce multiple blocks where only one is taken. And you have a lot of different things to keep track of. Which variable aliases another variable. In case of bailout, what do you restore for the interpreter? This is really non-trivial. The JIT also has to model perfectly what will happen in case of in situations where it might fall back into the interpreter, because you don't want the JIT to assume that nothing is going to change when the slow path might actually change some internal data structures. It also does some range analysis for bounce check removal, which sounds really scary, and a lot more things happening. So there's a lot of things that can go wrong. And now a quick slide about the desktop pass, which is the last pass that's run by the global optimizer. Once again, not really interesting for us. It's the same algorithm as the first backward pass, and it's mostly there to remove what's redundant, such as type checks, which might be redundant because the thing is checked higher up in the CFG. And it's not super interesting if you're looking for bugs, because most of the bad decisions that will be taken in the desktop pass will be as a consequence of bad things happening in the forward pass. So yeah, so finally we get to a bug that I will walk through with you. It's a bug I reported to MSRC last year. It's a JIT bug, of course. I found it with fuzzing, which I'm not going to discuss the approach at all because it's too complicated. I will talk about that at Infiltrate if you want to check it out. It was fixed last August, and it basically relies on what I talked about, the JIT not basically accounting for certain internal things that can change with JavaScript operations. So here on the left, I have some JavaScript code. I hope you're quite able to see at the back. And we'll basically walk through that together. But the thing is, if you took that code, run it on a reuse build of Chakra Core, which is vulnerable, well, you will basically observe the following crash, where it's basically trying to move whatever is in RBP inside what looks to be an array access with RAX holding the base of the buffer. So if we look at the value of the two registers, it's trying to move 1, so the tagged integer 1, which is probably what we have on the left, O.E equals 1, so that's where the 1 comes from. And the RAX, the base on the base of the buffer, is x414141 with the tagged bit set. And we basically see as well in the JavaScript code that we actually set a property to x414141, so it seems to be correlated somehow. And basically what you gain as information from that crash, if you're familiar with Chakra, is basically that somehow the pointer that points to the property values has been overwritten by x4141. So just a quick refresher, that's one of the slides that we saw right at the beginning. They have this layout that's called object header inline, where basically the property values are stored directly inside the object itself. And we'll need that because the bug is actually related to that. So here I will walk through basically what happens in the JavaScript code. So first off, we see that we declare this function opt, and we basically have a loop where we call the function repeatedly with the same kind of scalar object, which has 3 properties, A, B, C. And why we do that is basically we want to optimize the code for that particular type of object. Now what happens is that in the code we access some properties to set the symbol as live. This is not super important, it's just because you want the optimization to take place, so you need it, but it's not really relevant to the exploit itself. And then we add a new property, property E on the object that we set to 1 in the code. And we repeatedly, property E is set in an anonymous function that I call repeatedly inside a loop. And we call that function and we set property A all the time to x for 1 for 1. So what I want you to take away from that is basically, like, it's not meaningful JavaScript code. I doubt that you would ever write that if you write JavaScript for a living. But it's not ludicrous code. Like, it does not rely on any of the crazy things that you can have in JavaScript, like proxies and stuff like that. So why do we have a bug? Basically, why do we have a crash? Well, the key is in how these two objects basically differ and how they will behave when you add property E to it. So to highlight that, I have here an object which is similar to the one I passed to the function when I optimize it, which is an object with like 3 properties, a scalar object. And if you look in memory how it looks like, you basically see that you have the properties stored directly in the object, so you can find the value in blue. And now I add a fourth property, property D, that I set to 4444, and if we dereference memory, then we can see that 2 things have changed. First off, we have the property 4444, which appears where we expect it to appear, and then we have the second pointer that has changed. So this is the type pointer, and of course it has changed because since we added the property, the type of the object has changed. But nothing crazy. Like the key takeaway here is that adding a property to it actually doesn't change the layout of the object. Now what happens with this object, which is a scalar object, but this time has 4 properties. So if we look in memory here, we have the same thing. We see our 4 properties appearing directly inside the object, as you would expect. And now we add the 5th property to it, so property E that I set to 4545. And now if we look in memory how it looks like, we see that everything has moved. The second pointer has been updated as before, and now we have a pointer where x4141 was, we have a null pointer where x4242 was, then we have x4141, x4242, so those have been like moved by 16 bytes. And if we dereference the pointer that we saw appear, we basically find the rest of the property values. So this is the oxlos pointer. We're looking at the thing that points to the property values. And the takeaway here is that we still reuse some of the inline space that we had allocated because let's not waste it. But the thing has completely changed. Instead of having all the properties stored inline into the object, we now rely on that external storage through the oxlos pointer to store the property values. So maybe you kind of guessed like the problem already. So here, when I set property E on my object, which has 4th property, which is just what we saw, that will actually change the layout. Now, what happens if the JIT compiler, for some reason, failed to say, oh, this might actually change the layout, I better redo the type check or actually account for that. So what happens is that Chakra just like, under this particular situation, just like thought, okay, this is fine, nothing is going to happen. Well, when we come back from the function, after we change the layout of the object, this will just like write at a direct offset in memory, as we've seen in the example. And that will write where O.A previously was, which is where the oxlos pointer now is. So this is basically the bug in a nutshell and why we observe the crash. So the primitive we have is we're basically able to corrupt the oxlos pointer of an object with a JavaScript value. We have a couple of problems associated with that. First off, we cannot set it to a raw pointer directly because every integer or double that we produce from JavaScript will be stored tagged, so that's not going to be a valid address. We have the same thing then to write arbitrary values. So we basically need to further corrupt other objects. And if you've looked at any kind of JavaScript exploit, you've probably seen array buffers and typed arrays, which is the best gift that could have happened for us. So now I walk through basically the full exploit to get a full read-write primitive from that. I will release the exploit code, so like if you want to check it out for yourself later on. So here I have an object. It's a global object. I declare it right before I even declare the function. I set a certain bunch of property to it, and I also declare a global array buffer. So nothing crazy so far. And now I use the trigger that I highlighted before. So I just changed 2 things. Instead of setting O.A to x414141, I set it to my global object. So basically, when we trigger the corruption, the bug, this is basically the memory layout that we achieve on the right. We have object O that basically points to the global object itself, but directly inside it. And now when I run O.t equals target, I'm now able to further corrupt the global object and make its sockslots pointer point inside the array buffer itself. So all in all, basically, like right after we triggered the bug, this is the memory layout we have on the left. We have our two global objects, and my global object points directly inside the array buffer object. And the array buffer object is really interesting because it has a certain field, which is like the buffer pointer, which points directly to memory, where you read and write from when you declare a typed array on it. But we still have the same problem, which is even though I could corrupt everything that's inside the array buffer, so I can override the length field to get an out of bound, we cannot completely control the pointer, and we want to read and write from memory arbitrarily, not relative to the buffer itself. So we need, again, another corruption. And this is really simple. It's only two lines of JavaScript. I just declare another array buffer. And since I have the ability to overwrite whatever is inside the target array buffer, by just executing obj.h equals hacks, which is the new array buffer I created, we basically achieve this memory layout, which is we have an array buffer of which the buffer pointer points to the inside of another array buffer. And what that gives us as primitive now is that we can create typed array on the target array buffer to completely corrupt the hacks array buffer. And typed arrays are really good because with typed arrays, you're not dealing with tagged value. Like the integers or the doubles or the floats you're generating will be stored completely unboxed. So that basically gives us the read and write function. So these are really simple, like 5 lines of JavaScript. So if you want to read and write from that point on, basically the first thing you do is you declare a view on the target array buffer. So you declare a typed array on it. The first thing you do is you overwrite at offset 14 and 15. This is where the buffer pointer will be. Doing that will basically control the buffer pointer of hacks. And now you just have to declare a typed array on hacks, and you can read and write from memory anywhere. So that's basically a full read-write primitive. You're not quite done if you're looking to do a full chain, but this is not to talk about exploitation on Windows. If you want to check that out, Sar gave an amazing talk at CCC that you should check it out, which will have much more information. But it's still, like, getting full read-write, it's pretty good. It's what you want, basically. So yeah, there you go.